Okay, morning. Okay, so I know that there's a midterm tomorrow, so at 8 o'clock, and make sure you rest early today and get up. Actually, I'm reminding myself. So, yeah, lots of students come and ask questions, but I do notice one thing though, Yeah, the concept. So when I ask this, when you ask a question and then ask back, I said, what is the impulse response? So this simple definition, a lot of you got stumbled right there. You started, oh, that's derivative of something. That's not impulse response, right? No. Impulse response is when the input is impulse signal. That's as simple as that. Okay? Yeah. So those basically when you prepare, not just doing the question, make sure you see the concept behind the question is fully understood. For example, what's the definition of the impulse function? Can you write that down? Right. And what's the definition of a unit step? A signal. Okay, so those are simple ones. Make sure you don't stumble over there, right? Yeah. When you're saying, I sort of got it, that basically means you're not fully getting it, right? Yeah. So you don't want to say sort of got it, okay? So exam is, not a just water, right? It's blank. So exam always I'm trying to put in is a little bit what you call curveball, right? But nothing actually as tricky as that you haven't never seen before. It's always around the concept or the questions that you have done. Okay? So when you're doing it, make sure you fully understand the principles and the ideas behind it. Okay? Not just question by question. I understand the question now, but then the question changed, right? So that's important. Okay, so let's continue on 248. Okay, so we're going to talk about interesting concept today. It's just the mean max problem and the constrained, unconstrained problem. Okay, so this is actually, it's actually the first time I'm teaching this constrained, unconstrained. In the past, I never touched this before. So this is more of a related to optimization problem. Okay, so first, let's talk about the mean and max problem. So mean and max, more of a, we call it extreme values and settlements. Okay, so what this means basically, it's actually quite simple. Let's use function of two variables, for example, right? So if I have a function of two variables, then I can sketch that. We know that's a surface. So the surface may be looking like this. Okay, so there might be a surface here, basically. So that's this kind of surface we're looking at here. It's up and down mountains, right? Now, when we look at this surface here, and apparently what I would call this, I would call these points here, okay, extreme points, right? Extreme points. So basically, these points are extreme points. Yeah. So, if more specifically, I guess, if I look at this point here, I can also call them local minimum or local maximum. Okay, yeah. So the key word is local, right? So what does a local mean? When I look at this part here, that's the maximum around this local, basically. right? And this is the maximum around here. And this is the minimum around here. So that's why we call local minimum and local maximum, right? Okay? Now, so if their wording is a local, then there must be a word called global, right? So the global minimum, so those are, this is A, B, C, right? This is A, B, C, are local minimum and local maximum. Then we must have another one here called global minimum or global maximum. So, yeah. Or this one here, yes. Yeah, that could be one local minimum there. Yeah. Good point. Yeah. But I guess you get the idea now, right? So when you're looking at a minimax, so if you look at the very small region, you find the minimum, right? Okay. However, if you look at the full region, so full region basically means it's the region, right, for x, y, for x, y. So where does x, y, where are x and y defined? That's basically what we call the region. So, you know, if a single variable, say x is defined between 2 and 3, right? That's the region. And for two variables, maybe x and y is defined, x is 2 and 3, y is between 3 and 4. So that's the region, right? Okay. So within this region, let's say for this drawing I show here, the global minimum or global maximum will be simply the B point here, right? So the overall, the B has the maximum value. And global minimum will be the C point at here. Okay, so that's this concept of global minimum and global max. Okay. Okay. So there's another word in here when we talk about extreme values, right? Extreme values. So you can pinpoint as a mean or max. However, if you recall that for some other surface, so for example, the surface, we call that z equal to x squared minus y squared. If you recall that, what kind of surface do we call that? Saddle, right? That's a saddle surface. But this surface here, there is a point. Why is it called a saddle surface? Because there's a point on the surface, right? There's a point on the surface, and if you go from that point to certain direction, it goes up, right? But if you go to another direction, it goes down. So basically that point, okay, doesn't really tell you whether it's a minimum point or maximum point, because you can't decide, right? Not like the point over here. If you're at A point and B point, and you move yourself any directions you want, right? Any directions. The surface always goes down, right? Always goes down. So that's absolutely the maximum point. But if it's a saddle point, right? I don't have a drawing over there and a saddle drawing there. So if the saddle point, yeah, it's more or less like that, right? There's this point here. You can't decide. If you move around yourself at that point, right, you can't decide. So this is called a saddle point. So in this case here, we can decide that. As a matter of fact, if you recall that in single variable system, you may come across a kind of a function like this. This is just an example. This is like y equal to x, c. So right here, right this point in here. If you move this direction, it goes up for this curve. But if you move this direction, it goes down, right? So for single variable, remember what do we call this point here? Okay, so this is those are situations, you may encounter, okay, when you have a function of two variables. Okay? Yeah. Now, doesn't matter whether it's a local mean, local max, global mean, global max, or saddle point, okay? And for all of these points here, we have a name, big name, we call them critical points. Okay? So for all of these ones here, we call them critical points. Okay, critical points. So why is it called critical points? Right? So the critical point, the meaning basically means at that location, whether you are here at the saddle or whether here. And what happens is the function, this function f, which represents this surface, right? It doesn't increase or decrease anymore at that location. That's basically what happens. Right? It doesn't matter whether it's a mean or max or saddle. It's giving a very small distance, appears it's flat at that location. Okay? So we call them critical points here. All right. So now, come to the question now. So how do we determine, a critical point given a surface? Okay. And how do we determine whether this critical point is a global mean, a global max, a local mean, a local max, or is a saddle point, right? So that's basically the first problem we're going to solve it here. Okay. So we're going to determine. So we're going to looking at two problems here. First, we're to determine critical points on a surface. Then we're going to determine whether it is mean or max or saddle. Okay? Yeah. So this is the first objective of this lecture here. So let's talk about how do we determine the critical point? How do we find the critical points on the surface? So here's the z equals to f x y surface here, right? Yeah. I think I mentioned this in the end of the last lecture. So basically, the whole idea is from the definition of critical point. Critical point is the point on the surface where there's no change of this function f, right? So, in the previous lecture, we learned how do we describe the change of the function f? Grading. So basically, at this critical point, the grading of the function f will be 0, right? That's the obvious fact here, because grading of the function f points to the greatest increase of the function. And now, if there's no increase, then there's no increase. There's a critical point. Okay, so the first point here, so del f equal to 0 will give us critical point. Critical points. Now, gradings, grading what it is. It's df over dx, if plus df over dy dz. That's grading. Now, if you recall that in the single variable case, how do you determine whether it's a critical point? What do you do? What do? You take a derivative and you let it equal to 0, right? That's how you determine the critical points. So what we call this one here, so you look at this one here, what happened here? You have to do derivative, right? And then you let it go to 0. So that's basically what happens over here. That's essentially the same idea here. So what we call this one here, we call this the first derivative test. Okay? First derivative test. Know what I mean? Like my salad? Oh, you're not talking to me. interesting. Okay. Just in case no massage is good. Okay. Alright, so now let's go back over here. Okay. Now f equal to 0. So what does that mean? This factor equal to 0, right? So this factor equal to 0 means we are going to this one here. Okay, this one here. Okay, that's good. So this is the first derivative test. It's like you're doing here, right? Like this one here. That's pretty simple. Okay, let's understand here. So check these two first derivatives. So essentially, you solve these two functions. You solve for x and y, so you get all the points, so the critical points, the coordinate critical points. So that's all of the first question there. Okay, so okay, so second point is, how do we determine whether that critical point is a minimum point, maximum point, or saddle point, right? Saddle point. So the second one here, now we're going to talk about a theorem. Okay. So this theorem essentially, let's come back to the here, right? Let's go back here. Now if you recall that for single variable function, how do you determine whether you solve this one x for the function? And then how would you know this x, the value at this x value here represents a minimum location or maximum location? Second derivative, right? Yeah, you take a y double prime and you look at the sign of the y double prime, right? Yeah. So same thing here. We're going to use a second derivative test. Okay, second derivative test. Yeah, but it's just a function of a two variable, so it's not going to be as easy as just y double prime. So here's the theorem. It's a bit of long. Now, what happens here is you need to be the second derivative test will give us this local. So basically, it's a local extreme value. Okay? So we have to look at the whole result in order to determine whether we got a global or not. Okay, so here's a theorem right down here. So suppose this function has first and second, okay, partial derivative. So basically, it's a continuous one, okay, continuous in terms of first and second partial derivatives. Because if it doesn't exist, then we're going to have trouble. So another case. And then at a certain point, okay, so from the first limits at here, we're doing first derivative test. So we solve these two equations that are here, right? So suppose the solution of this one here is this solution here. So basically, at this point A, point B, your first partial derivative, okay, is 0. So now I'm going to write here. So this is 0, and this is 0. Okay, so the first partial derivative 0. Then we have 4 different situations for the second derivative test. Okay, 4 different situations. First one is f has a local minimum, okay, at AB, so if fx is less than 0, and okay, and down here, and fx x fyy minus fxy squared greater than 0 at AB. Okay, so that's the first situation. So let's look at this guy here. F has a local minimum at this critical point AB if the second partial derivative, fx, is less than 0, and this guy multiplied by this guy minus fxy squared is greater than 0. Okay, so that means this point AB will be a local minimum. Okay, will be a local minimum. Okay, yeah. So as a matter of fact, if you go back to single variable here, when y double prime is less than 0, that x is the local minimum, right? Yeah. So when you have a function two variable, so you had one more condition in here, which is this guy here. Okay? Yeah. That's the first bullet. Second one, f has a local maximum at AB if fxx is greater than 0 and fx fyy is greater than 0 at AB. Okay, so that's the second one here. Yeah.
That is fxy squared. Does that assume that fxy is the same as fy?
Yes. Yeah, so it will be continuous, so fxy will be the same as fyx. Yes. So the second bullet, the only difference from the first bullet is this term. Okay, this is greater than 0, and this is less than 0. And the other condition is the same thing, so greater than 0 here. Okay, greater than 0. Okay. Third, f has a saddle point at AB. Here is fxx fyy minus fxy squared 0. Sorry, less than 0 at AB. Okay, so that's the third condition. So the third condition, only looking at this one here. When it's less than 0, it's going to be a saddle point. Fourth point is the test. It is inconclusive. And inconclusive at AB. If this guy equal to 0. Okay. So this is a theory. It's pretty long theory. Okay? So you will have this formula in your final exam, but the key point is how do we make use of it. Okay. Yeah. So let's take a look at this four situations that is here. Okay? Four situations. This seems to be coming out of nowhere here. Actually, I can prove that very systematically using Taylor series expansion for multivariable functions. So if you're interested, I'll show you here, okay? Yeah. So I'll save myself the writings, basically. Okay. All right. Is this okay? So when you look at this theory here, right? You know, first thing you maybe ask yourself is, does all the symbol looks familiar to you? And are we going to be able to calculate each one of the quantities given enough conditions? Right, so that's basically the first thing here. Okay, so let's take a look at examples here to look at how do we solve this problem. Before we go on here, well, let's see. Let's maybe take a look at this first and second here. First, second, okay? Yeah. So when you have a single variable function here, y double prime less than 0 or y double prime greater than 0, what does that indicate to the curve? So yeah, if you have a y double prime less than 0, the curve is keep computing up or down. So for this case here, the curve will be like this, right? And this for this guy here, it will be like this, right? So same thing over here now. So if I look at my first and second, when I look at oh, sorry. So I think I got it the way down here. So the other way around here, right? It's the other way. Okay, the other way. So if I look at this one here, you see, this f is a local minimum, and that's when fx is less than. Oh, I guess I was right, right? Hang on a second. Local. No, I was right. Yes, this is right. This is right. This is right. Yeah, this is right. So when this is the case, when fx is less than 0, it's a local minimum. So local minimum for a surface, it's basically a surface with what kind of shape? It's a concaving downward, right? It's this kind of shape, right? It's this kind of shape. So the am my logic okay? Huh? I made a mistake. Where?
In the book it says it's just opposite.
It's the other one, is it? Yeah. Oh, okay. The other way around. Huh? Come again?
For local minimum, fx should be more than 0.
You mean here is greater than 0? Oh yeah, you're right. Sorry about that. Absolutely, yeah. So yes. So sorry about the confusion here. Yeah. So when fx is greater than 0, you have a local mean. When fx is less than 0, you have a local max. Okay? You have a local max. Okay. Good. Yeah. Very good. Okay. So basically, when you have a local minimum, your surface is always kind of surface like this, right? This kind of surface. So in mathematics, when you have this kind of surface, this is called a convex. It's called a convex. And the second one here, you have a surface like this, right? More or less. Okay? And this kind of surface is called concave. Concave. So if you go to a mathematics department, so there's normally a course called convex optimization. Yeah, so then when that kind of course dealing with basically, it's always kind of surface like this kind of thing situation, convex optimization. Well, we're talking about a function of 2 variables, right? So you can have a function of a 3 variable or even more than 3. So this convex or concave, not necessarily restricted to this surface here. It can also be extended to so-called hyperplane, hypersurface. Okay? Yeah. Hang on a second here. Why? No, this is mean, right? Mean is convex. Well, see, you have a bar, right? Let's say you have a bar. When you bang the bar, let's say you bang the bar like this, it's called what? Concaving. That's concave. Okay, that's possible. I think I'm going right. Yeah. This is convex. We'll talk about that after class. Yeah. It's not upside down. Yeah. So, okay. So now I think we got everything right in here. Okay, we got everything right here. So now let's look at examples. Okay, here's the surface. And let's try to find all extreme values. Okay, so not just extreme values, okay, but also determine whether they're going to be local mean, local max, or saddle. Okay, so this we're going to do. So we're going to strictly follow the theories we just presented right here. Okay? Yeah. So what do we do first? We first do the test first, right? To find a critical point. Okay. So LF equals to 0. Partial F over partial X is 0. And partial Y over partial Y, partial F over partial Y is 0. Okay? So let's say what's the F in X? So taking 24x cubed, x squared, 0, and 6y. So that's the first equation. Second equation, this is 0, 3y squared plus 6x, that equals to partial 0. Yeah. Okay. So solving the two equations that are here. Using substitution, you can let x equal to substitute in the solve. Okay, so this is not a linear one, but you will be able to solve that. And we'll be able to solve this. We can get two solutions for x. One is 0. One is negative 1 over 2. Okay. Yeah. Anyone want to go over the steps? I think you can take a look at how to solve this. Okay. So when you have x equal to 0, x equal to negative 2, so you're going to have a different y values here, right? Yeah. So when x equals 0, you can find y is also 0. So when you substitute x equal to 0 here, so y is 0. And you substitute negative 1/2 here, right? Because y is negative 1. Okay. So in other words, the critical point we're looking at, right? The critical point, there are two critical points. One is 0, 0, and one is negative 1/2 negative 1. So there are two critical points. So the question comes to now, what are the critical points? Are they local mean, local max, or are they saddle points, or the sum site? Right? So now we take second derivative test. So second derivative test, let's come back here. So what do we need to calculate? I guess we need to calculate fx, x, and we also need to calculate the quantity of this one here, right? Okay. So now we need to calculate a couple of things here. So we need to calculate first what's fx, and what's fyy, and what is fxy. So we need to calculate three quantities here. So fx, okay, that's going to be calculated based on the results over here. Not fx here, right? This is fx. So partial that over x again. Fyy, calculate that based on here. So that'll be 6y. And fxy can be calculated based on either one of this is good. So that'll be the 6, right? Okay. Yeah, that's right. Yeah. Yeah. So now we got all of this one here. We need to calculate the values of these quantities. So this value at each one of these critical points. So let's separate the situation here. Let's separate the situation. And so I'm going to use the two for 0, 0, and here is for negative 1/2, negative 1. So fx will be the same as 0. Sum this x of 0 over here, that's 0. And for this one, fxx, so you sub this 1/2 negative over 0, and it's equal to negative 24, right? Negative 24. Okay. 0 for this critical point, fyy for this critical point, negative 1, here, negative 6. fxy, it doesn't change, no matter. 6 here, and 6 here. Okay, so now we've got all the quantity, and we're ready to do our second derivative test. Okay, yeah. I guess we need to calculate one more quantity here, right? The other quantity is fxx fyy minus fxy squared. Okay, we need to get the value of this quantity. So here and here and here. Okay, so let's see what this is equal to. So for the first critical point, this expression equals 0, 0, minus 6, so equal to minus 6. Plus 6 squared, of course, 30. And for the second one here, okay, that you might need to use a calculator. 100.08. Yeah. Yeah, so this is 36 positive 144 minus 36, 100.08. So now we got everything. Now let's apply this second derivative test. Second derivative test. So second derivative test require us to do what? To check the sign of fxx. To check the sign of this fxfyy minus fxy squared. So let's look at this one here. Okay. So second one for the first critical point. Since this guy here minus fxy squared is less than 0, right? So less than 0. Okay. So now let's go back to our theory here. Okay. Which one has that term less than 0? The third one, right? The third one. So the third one doesn't really care what fxx equal to. You only look at if this guy is less than 0, and then it's going to be a saddle point. Okay, so which means this is a saddle point. Okay, so this is 0, 0. Okay, so that's simple. And this one here, we find that fxx is less than 0. And this fyy minus fxy is greater than 0 because 108. So overall, what kind of point is it? Local maximum, right? Local maximum. Is that right? Yeah. Because local maximum is when fx is less than 0, and this term is greater than 0. So this is a local maximum point. Okay, local maximum. So that's it. That's basically what happens here. Now, if the next question is, what is the local maximum value? What is the value at the local maximum point? What's the maximum, local maximum? You said it's the local maximum, so what's the value of the surface, right? So what do? We plug this x and y value into the original surface, and you calculate. So the value you get here, you can get is 1. Okay, so the maximum, local maximum value at that -1, -1/2, -1 is 1 at here. Okay. So it's actually not very tricky in terms of the calculation. Okay, so you just follow the steps and compare to the theory and pinpoint which kind of a point it is. Okay, any questions? Yeah, and I can see what it looks like. Here, this is what a surface looks like. Okay, this is what a surface looks like. So you can, so you see the surface here. There are 2 points here. This is a 2 points, 2 critical points. So can you guess which one is the local maximum? Which one is the saddle? Yeah, the one on the right is the local maximum, right? Yeah. Okay, good. That's it. That's basically mean and a max here. Mean and max. Now, we were talking about the first unconstrained here, right? So if you look at this one here, this is basically a so-called unconstrained problem here. So you see the surface. You want to determine the local mean, the local max. That's basically so-called unconstrained. Okay. So what we just had is, so find the mean or max equal to fxy, okay, can be called as a unconstrained problem. Unconstrained problem. And this is basically a sort of optimization problem. You know, optimization normally is what happens is you go to a factory and so the guy says, okay, can you minimize the cost, right? Okay, then they said, okay, what's the cost function? The cost function is this guy here, right? So then you say, okay, I'm going to calculate the mean value of this one here, and I'll tell you at what x and y value you can minimize to. Maybe x represents the money, y represents the labor, or something like that, right? So that's basically optimization problem. Now the next one here is, right, things are not always so shiny, so there's always constraint, right? There's always constraint. So now here comes the thing here, unconstrained. That's basically unconstrained. This is constraint problem. Okay. So in general, this kind of problem is the objective. The objective is still trying to maximize, okay, this z equal to fxy. Okay, so you're still trying to do this. Okay. However, now you know that not just trying to minimize it. You have to be careful. It's a subject to certain condition. So subject to it, okay, condition, which is basically the constraint we were talking about here. Subject to constraint here. So what's the constraining? And we still use a function to represent a constraint. So here's constraint. Okay. And C here is a constant. C is a constant. So that's the more general problem here, right? So let me give an example here, okay? An example is before we move on to solve these kind of things here. So for example, reading a wall here. Okay, so then this side is W, this side is L, right? This side is W, is the L. So the way that you want to build this, okay, you want to design this guy here, area is 15 square meter. So you want it to be always 120 square meter. Okay? Let's say not a wall, let's say a fence. Okay, the fence here. You're going to use the wires to build up this fence here, right? So the fence area is always 120 square meter. However, what you need is what you know that is material for this for the bottom side here, for the red side, for the red, is $50 per meter. Okay. And the material for the blue side, okay, is $3 per meter. Okay. So the Home Depot says the steel fence like that. Okay. Then the whole question here is, okay, how do I minimize the cost? All right, how to minimize the cost? Pardon me? Okay. So let's say if this is basically the kind of constraint problem we're looking at here, right? Here. So first of all, what's the cost here? All right, what's the cost? Let's say if I use a function f to represent its cost, right? To represent its cost here. So how do I calculate the cost here? Red, $50 per meter. Blue color is $30 per meter. The length here is L. So blue color is 50 plus what? Yeah. 30 by 2 by W, right? So there are two W's here. Right? And the top is also L. So the cost of the top is 30L. Is that clear? Okay. So overall, this is 80L plus 60W. Yeah, 60W. Is that okay? Any questions? Yeah? It's all good, right? Yeah. So that's the cost here, right? Or that's the function you're going to minimize. Okay, that's the function you're going to minimize. And what will be the constraint then? The constraint is you need area. You always 1200 square meter. So what's the area? So the cost, so the constraint, right, is the function E will be W multiplied by L equal 1200 square meter. So this is basically exactly what happens here, right? So this is the constraint. Okay. And this is the objective function. So the constraint here sometimes, yeah, this is a little bit different. This is already minimized, but constraint is the cost. There is another word called cost function, or sometimes we call it performance index in optimization courses. Okay? However, remember this constraint here, okay? Yeah. So if you have never learned what I'm going to show you, and what do you think you're going to solve this question here? Mish, right? Yeah, yeah. Yeah, that's good. So she said, she's going to solve for one variable from here and then plug it over here, right? Yeah. So when you plug it here, instead of two variables, you're going to have just one variable now. And it's just one variable, and then you can use single variable function to solve for the mean and the max, right? Yeah, so that's an easy way of doing it. Substitution, right? Okay? Yeah. Good. So the only thing is, this is a simple case, right? A simple case. What if my cost function or objective function is not as simple as this? Then, for example, maybe here is a W square or even square root of W or something, right? Then it's going to be very hard to solve for one variable and plug it into the other one, right? That's the situation. We need a better approach to this here. Okay. So I have another example, but I think I'm going to skip that, so we're going to talk about that. Okay? So let's see, what do we do? Okay, what kind of approach shall we use to solve this kind of situation? Before we move on, and let's rewrite this, the two things here. One is fx z equals fxy, and the other is gxy equals c, right? So we're looking at these two right here. Okay, we're looking at these two. Okay, so p of xy equals to c. And this guy here. Now I need to understand a couple of things based on what we learned. First of all, if I just look at the p of xy, that's a function of two variables, right? That's the surface. That make sense? Right. Now, when I let the surface equal to 0, remember what does that give us physically? This one here. It's called a level curve, right? A level curve. So this guy here basically is a curve. It's a curve. Okay. And where's the curve from? The curve from this E of x, y, right? Equal to c. Right, so essentially, let's see, I'm going to say here, maybe this is your g of x, y equal to c here. Okay? Now this is within the xy plane, that's your constraint, right? So now you can say that, what does constraint mean? Constraint basically means your x and y value are not going anywhere but along this curve. Okay? That's the constraint. Okay? Yeah. And then you have the surface fxy, right? The surface xy. So the surface xy maybe, let's say I'll just arbitrarily draw something here, okay? Maybe it's somewhere here. Okay? Yeah. So that's kind of situation we're looking at here. So then you can think of this finding mean or max of this constraint problem as if you're doing this. You are, trying to walk along this curve C. Yeah, let's call it curve C. You're trying to walk along this curve, right? As you're walking along this curve, imagine there is another guy right on the top here, right? Right on the top. So you're controlling here, A controlling the B, so this B is going to follow this A right here. Then, as you're going along here, guess what? This B will somehow trace out a certain kind of curve, right, on the surface. Does that make sense? Yeah. Then, finding the mean or max is basically you're looking at where the mean or max of that intersected curve. That makes sense? Right? So you're walking here, but you're also walking along the surface. Right? And somehow there will be a curve traced out along the surface. Then where is the mean and max of the curve? That's going to be basically the solution of this problem here. Right? Yeah, because you are moving along this curve here. Right? Okay? Okay. So now back to another idea here, right? That's another idea. How do I know the rate of change of this curve? Now, if you remember, when we learned the directional derivative, right? What do? I said walking in the direction of u hat, right? Then I will get a certain rate of change of the function f in that direction u hat at a certain point. That make sense? Okay. So I can have a rate of change of f, right, in u hat. So this is the general thing here. So I'm writing down the formulas, but that's basically the idea of directional derivative, which is what? df over ds u hat equal del f dot u hat. That's direction derivative, right? That's direction derivative. Okay? So now come back to this question here. What does u hat mean? U hat represents the direction of walking, right? Direction of walking. So where are you walking? You're walking along this curve. So if I say, okay, right now you're here, what will be the direction of walking? It will be here, right? It will be here. What is the relationship between this u hat and this curve G? Longer. Tangent, right? So this u hat must be tangent to this G here. Now, okay. So the question is not the general directional derivative. Alright? We have some couple of properties of directional derivative. So directional derivative is the rate of change of f in this u hat with respect to certain displacement. Yes. So then what happens if df over ds equal to 0? Right? What does df over ds equal to 0 means? Right? No change, right? So basically, the rate of change is 0, so there's no change. No change. If there's no change, So mathematically means what? Where are you? You're at critical point. Right? So basically this means it's a critical point. Okay, critical point. Maybe the mean or maybe the max, right? Okay, so that's great. All I'm trying to do now is I'm going to try to calculate this directional derivative net equal to 0, right? And I will be able to find the critical point while I'm walking along this curve D. So if this is 0, what's the relationship between del f and the u hat? Perpendicular. So del f is perpendicular to the u hat. Right, so follow my logic here. Every step is it's already proved. Okay, there's nothing new in here. So del f perpendicular to u hat, that's the condition. Give us a critical point, right? Give a critical point. And what is the relation between u hat? U hat is tangent to g. Now, what would be the relationship between del g and u hat then? We had one of the theory when we learned this grading vector. When you calculate the grading vector of this function f, now it's a g, right? This grading vector is perpendicular to what? To the level curve, right? To the level curve. So, what's del g here? Del g is the grading vector of function g, right? According to a theory, the del g is perpendicular to level curve. What's the level curve? Level curve is Cxy equal to 3. That make sense? So if del g is perpendicular to level curve and the u hat is tangent to g, then that means del g and u hat must be perpendicular. Right? Must be perpendicular. Yeah. Sure. Yeah. So this is u hat here, right? So the del g maybe goes this way. Yeah. Is that clear? So we're almost there. So now look at all the given conclusions here, right? Del f perpendicular to u hat. Del g is also perpendicular to u hat. And all of this point here, where's del f? Del f is also a vector in the xy plane, right? I'm not sure where, but it's going to be inside xy plane, right? So 3 vectors in the xy plane. Now you tell me, what will be the relationship between del f and the del g? Same direction? Or more precisely to see? Right? Parallel. Now remember what del is a vector. Del g is a vector. When two vectors are parallel to each other, what's the difference? Multiple. So they are just a multiple of each other. Now this is a very important conclusion. This what's coming next is basically all based on here, right? Yeah. So think about what happens here. And think about this whole logic that we just gone through it here. Okay? So basically, you need to ask yourself, where does del f parallel to del g from? Why at the critical point del f is parallel to del g? That's the here. Okay? So if I go through again, u hat is the direction walking. And naturally, the del g will be perpendicular to u hat. And del f is the grading vector function hat. In order to find the rate of change of f, we have to find the location where the directional derivative is 0. Directional derivative is 0 meaning the del f is perpendicular to the u hat. del f perpendicular to u hat, del g perpendicular to u hat, meaning the del f is parallel to del g. Two vectors parallel to each other, meaning they're only a difference of each other, a scale difference. So we actually can use a negative here, okay, for ease of the writing here. So we use a negative, it just doesn't matter here, okay. So the lambda here is just a parameter. So you can use anything here, okay, you can use anything. However, people giving it a name now. It's called Lagrange multiplier. Okay. It's Lagrange multiplier. So this multiplier here, not quite clear yet, but once I write the next one here, you'll see that why it's Lagrange multiplier. Okay? Yeah. Okay, so I'm going to show you one more thing here regarding this one here. Okay? Yeah. So this is basically what happens at critical point. Walking along this EXY equal to 6. Okay? Walking along the EX equal to 6. So at this critical point, you have this condition here. Okay? Yeah. And the other thing is I'll show you using my lecture notes here. Okay. The other thing is at this critical point, or when the two greeting vectors are parallel to each other, the other point here is your constraint here. Okay, here's a constraint. The other point is the level curve of that function f, okay, will be tangent to this constraint at here. Does that make sense? Well, actually, it makes perfect sense because why? We just said at this point here, right? At this point, the del g is perpendicular to u hat. The del f is also perpendicular to the u hat. So essentially, the u hat is a tangent vector to both this constraint and the level. So if it's both of the two curves, that means the curve must be tangent at that location. Right? Yeah. So here's an animation I can show you it here. So let's look at this easy case here. Okay? This is the paraboloid that we illustrate some time ago. And now what I'm going to do is, here's my starting point. We're going to walk along a straight line. So that g of xy is a straight line here. Okay? So let's see what happens. And so we're going to walk in here. Okay, so it's going to walk along the straight line here, right? Yeah. So while you're walking along the straight line, then the function f will be basically traced out as a parabola here, right? Parabola. Now, if the question is, what's the mean point at the f while you're walking along this line, so the mean is going to be somewhere here, right? And somewhere here. Okay? Yeah. So you can see now, you see this circle here, that's the circle of the so-called level curve of this function f at this critical point here. Okay? At this critical point. So that's tangent to the constraint that you have it here. Okay? Yeah. Was that good? So I have another one here, but I think that we're going to see it later. Okay? See it later here. Okay? But overall, here is this one very good conclusion we just found out here. Okay? Yeah. Okay, so now what we're going to do is, so let's take a look at this one. Okay, let's take a look at this one here. What will we get from this condition? So we now have to put to this one because we're talking about two variables, but we give us function f over partial x plus lambda g over partial x equal to 0. And we give us partial f equals 1. y equal to 0. Is that it? Yeah. So this is great, right? Print and let the component of one vector equal to the component of the other vector. That's what you get here. Okay, that's what you get. All right? Yeah. Okay. So I guess we're not quite satisfied with this stage yet, so we're going to move one step further here. Okay, one step further. So what we're going to do is this. We're going to define ourselves a new function. Let's call it W here. So this W we can define as this. It's a function of, this W is a function of x, y, and lambda. Okay, so this function is y, x. These are the three things that are here. The function defined as this. Okay, here's what the function defined as. So, what's so special about this function here? So this function is actually quite good because why? Because it comes from your objective function and where? And also this is where from the constraint there, right? This is constraint here. Because when you let this term equal to 0, that's the constraint. Okay? And then this lambda that is here, multiply the constraint here. Okay? So this is actually why the multiplier here. This multiply comes from the picture, Lagrange multiplier. Okay? There's another name for this function. It's also called Hamiltonian function, but that's fine. Okay? Yeah. So why you define this function right here? Okay? The reason is because now if I ask you the question here, here's one function, right? If I ask you, can you find the meaning or max of this function W? What would you do? So basically you let del W equal to 0. Huh? So let's see. If we let del W equal to 0, what would we get? So del W equal to 0. X is 0. Partial W over partial Y is 0. And the partial W over partial lambda is 0. Okay? So three things need to be 0. Right? Let's calculate each one of this partial derivative and make it a 0. Here is your W here. What's the partial W over partial X? Here's F here, right? So partial F over X. Lambda is not, lambda considered as a constant. C is also a constant. So you end up with partial G over X. Anything? So we let it equal to 0. Okay, and then equal to 0. Second one, partial F over partial Y. Plus lambda partial G over partial Y, and we let it equal to 0. So what's the third one? What's the partial W over lambda? X, Y, and then that's it. Minus C equal to 0. Is that clear? Yeah. Yeah, it's a little bit intense here, so let's finish this portion here. We probably won't have time to do example, but so now you can see, based on the results of this, look at that. What does that tell us? The last one. What's the last one here? That's basically our constraint, right? And what's the first two right here? That's what I just showed here. And where is this from? From here. From this condition we find out. So in other words, so this genius guy, we find a way of combining everything into one thing. Right? So your original formula is find the minimum max of this function f, subject to constraint p. And now the question becomes what? Find the minimum max of which one? Of w. That's it, right? So in other words, you turn a constraint problem into a unconstrained problem. Right? So this right here is unconstrained problem. Okay. So everything boils down to solving these three equations, solving the three equations at here. Okay, solving the three equations now. Okay, solving the three equations. Well, if you can solve these three equations, and you will be able to find the mean and max, okay, at the f subject to the constraint g. So is that okay? Yeah. Okay. Okay. So. So a couple minutes here, but well, I'm not going to go over the example now. I think. I'll show you what this one here is, okay? What is this right here? All right, here. So let me write down a problem. Okay, so we're going to solve this for next lecture, but I'm going to show you this animation here. So here is this function f. Here is the constraint g. Okay. So in other words, here is the function f. So you're going to walk along the curve xy equal to 3. Okay, xy equal to 3. So if you can show you here, there are two vectors. The blue one is the gradient vector of this function f. The red one is this gradient vector of the function g. Now when I start to walk, so watch this transition of the two vectors here, right? Make a loop. So at somewhere, the two vectors become parallel to each other. Make sense, right? You can see that somewhere here it will become parallel to each other. And this is the traced out curve along the surface f. And this red colored circle is the level curve at the critical point. So that basically is what I showed you, the whole relationship between del f, del g, and stuff like that. Okay? Any questions? All good? Okay, we'll see you tomorrow.